distance is much smaller than r, r tilde and r become roughly the same. And we can, over the sum, already express this straightforwardly in terms of r. We don't even have to go through more complicated evaluation of this terms here. No? Furthermore, it turns out you can just express this in terms of the distance between the charges for the dipole. We also know that for the boundary condition, if you go to infinity, since the distances between charges shrink, it should look like as if it is just the sum of the charges put in a point. If this were a single point charge, you actually know where term, let's call it single point charge Q, you know actually how the potential should look like. Namely, this V from R anyone? Giving me some feedback. How does V from R look if I just put a single point charge at the origin?
0.
If I go to infinity, if I go far away, how does it behave?
For a dipole, it behaves like 1 over r squared.
No, not the dipole.
I'm sorry.
A single point charge.
Oh, because it's 1 over r.
Yes. No? K Q over R. Yeah? This is a single point charge potential far away from this point charge. This is always looks like this. If the single point charge was a collection of charges which result in an overcount of charge and I go far away, then it's the charge sum here. This little q is the sum of the q's, it's a monopole. Now, in this case, what is the monopole behavior of the dipole? I think you...
That one's the 1 over r squared.
Okay, but in terms of monopole, in other words, how much monopole behavior is in here? 0, no? Somebody said it already, I said, probably in misreference to the dipole, because these charges add up right there to 0. If I go somewhat away, the charges add up to 0. So in terms of monopole, I said this Q is the sum over the charges. Looked from further or far away would be 0. So in sorry. Oops. Sorry. So in terms of contribution monopole, kind of an academic question in a sense. Now, the dipole the dipole doesn't have any monopole behavior. So it doesn't behave as Q over R, and as you correctly stated, the potential rather goes with 1 over R squared. You have solved this actually explicitly in a homework. Just as a reminder, if I were to write it down, it's the sum of the contributions of the individual charges, no? So K, Q, and then 1 over R tilde plus, minus, because of the negative charge, 1 over tilde R minus. And now R tilde, which is R minus R prime, as I said, in the approximation that the R's come close to the R, we actually use geometry to describe the difference. But if I just shortcut this because we have done it, it reads like QK, K, Q, and then it had the distance explicitly in it, cosine theta, no? And then, as you correctly said, over r square. Important to notice, in fact, we describe this now in terms of the charge separation, as if we first deal with the charge distribution, or the distribution of the individual charges here first. We can plug this in, and then we get a different R behavior, in this case R square. In principle, we can continue with this. Say we have 4 charges, 1, 2, 3, 4, minus Q plus Q minus Q, and plus Q sprinkled around like this. Does this have a dipole, or does this have a monopole contribution? Far away out here, I look at this. Is this having a monopole contribution?
No.
Because?
At a large distance, don't they cancel out the charges?
Charges are 0. So no monopole. What about dipole?
Dipole is 0 as well.
Why?
So this one is a little tougher for me because the dipole is already neutral, so it can't be neutral.
Mm-hmm.
I would not know how to explain this.
Yeah, because if I would look like this, no? In principle, it looks like. Actually, let me first collect more input. Yeah. Any idea?
Does it consider 2 or 4 dipoles?
In what sense?
Considering that we have 4 particles, does that mean we have 2 dipoles of opposite charge that end up canceling each other out?
That's the answer. That's the sophisticated answer here, no? So in which direction do I draw the dipole vector? Just to indicate the 2 dipoles on this one.
It's
Which way would I draw?
You could draw them on the top. You could draw them on the top or the sides, but does it matter which one you choose?
No, I'm asking about the direction of the vector between these 2 charges. And then we talk about where all I place them. Let's indicate this one, the dipole moment between these 2 charges here. It should be here, but just to draw it out, which direction?
Up.
Minus to plus, no? This way. And then I have this one here. So I have a P1 here and a P2 here. They add as vectors, and indeed they're opposite. And now the question was, which directions should I choose, or which charges? So in this case, I assigned them to these sides, but the same holds true up here, no?
Does it
So
really
whatever-
matter what direction you choose, or can it, I mean, is it arbitrary? I feel like no matter what, as long as you have the addition, it's going to cancel out, right?
Here I have to be a little bit hair splitting. I'm drawing really by definition, the dipole moment, no? Dipole moment, that's distance, and then times the charge, but along which way? And it's the line from the negative charge to the positive charge, no? So it's a vector. Let's give it some, just to indicate this, yeah? So the magnitude is the distance times Q. In our expression, actually, it was already in here. And then the direction. Actually, in this case, if I choose the axis here as the z-axis, the angle theta with respect to the z-axis, then this is actually the scalar product, CR, no? And you have used this to come up with a coordinate system independent formula, where I do not yet define really in which direction I measure this angle. because ultimately it's just the angle between the r prime here that goes between the charges and the r which goes out here. And it becomes by chance the polar angle to the z-axis if I actually make the choice like this now. And so once we have defined it, we should stick to it. So now we have defined that it always runs this way by this, or let's say by this. No, this is inherent in here. Yeah, it goes along positive the z-axis, so it sticks up like this. Then I, of course, whatever. Yes, you're right. In this case, if I had forgotten my definition, it wouldn't have messed it up. But I wanted you to stick to the definition of the dipole moment.
But in general, the geometry of the situation can, in fact, change the quadrupole moment, or the dipole moment of the quadrupole. Like, just because in this situation it doesn't necessarily matter if we didn't take into consideration our definition, doesn't mean that the geometry and the definition that we set up won't change it in the future. Is that right?
The definition sticks with us.
Yeah.
Until you never have anything to do with electrostatics.
Okay.
Yeah, and so there are more complex combination of charges, and in particular, if I continue just so to say adding, now if I project this out in 3D, then indeed charges here, we still have no monopole, the dipoles add up, and in this case the quadrupoles, if I choose the charges alternating, you can think about it. So that potential is kind of straightforward, but in general, like just said, we want to of course deal with any combination of charges, and typically that results in a combination of these multiple moments. They have their contribution, and what is helpful to identify which one has the highest order, where do we start. If we have an overcount of charges, we can expect there will be a monopole moment at there, and the moment you have this, also because this is the one which drops off only as 1 over r, it has the strongest contribution. The next one is already reduced by another 1 over r. So this is, if we had really distinct charges, I started out writing the formula for continuous charge distributions, and so in principle we just have to formalize it the same way we did before. Instead of having a nice placement like this, we typically have some cloud. And the same idea now is that I place my origin close to the charges, say even in here in my cloud, and this asks me to integrate out the cloud. So somewhere here is my little volume element. I put my r prime here, and far away, the situation we're discussing here means the field point is somewhere out here, and the r tilde, that of course goes from any of these charges to over here. And now the idea is, if I actually integrate out here, the r comes close to the r tilde, no? R tilde again is r minus r prime, and we are looking at a situation where the magnitude of the r is smaller or much smaller than r. Now I can actually first make a series expansion of 1 over r tilde. That's pretty much behind the idea to arrive at what we call multipole expansion. Why? We will see this follows naturally, because if I do this, as you have read up on it. You can actually pull out the r. No, let's write quickly. So r tilde square. This is r square plus r prime square minus 2r prime cosine, and then the angle between these two, this alpha here, that's the angle between r and r prime down here. And so if I pull out the r here and then write this, get this as a 1 plus r prime over r square minus 2, and then again I divide out the r here, so r prime over r. R prime over r is much smaller than 1. I can read this as the 1 over r prime as a series as r, and then 1 plus epsilon. And now you know, of course, the Taylor expansion of this, which results in a form like this. So the 1 over r, we take it out, and if I write the rest, surprise, surprise, can collect the terms in such a way that it becomes r prime over r to the nth power, and then Pn of cosine alpha, where Pn are the Legendre polynomials. If this looks similar to what you have seen before exam, it's not a surprise. The 1 over r tilde is also called the generating function of the Legendre polynomials. So instead of using the Rodriguez formula, you could have also just gone through the exercise here and then collect the terms in powers of n. And you find, no? If you pull this r in here, it's actually 1 over r n plus 1. Look back at our formula. So r prime over r n plus 1. And then Pn cosine alpha, these are the Legendre polynomials. And accordingly, if I plug this back in, I write now my formula for the polynomial, this expansion, and actually it becomes the summation of 1 over Rn plus 1. It always goes 1 power above by 1 unit, and then R prime n, the Pn here, and then multiplied with rho r prime eta r prime. And before I start writing this out, I write only the first term here. So if you just take the very first one, with n equals 0 here, then this is just the 1 over r, r prime to the 0, which is 1, and then rho r prime theta r prime. If this is a simple charge addition, this is of course just a total charge Q. And this is indeed what we started out with. This is just a monopole term here. And accordingly, the next one, which goes with 1 over r square, will be exactly our dipole term where we add, where we integrate r prime and then cosine alpha. A quick remark, as you can see here, this is integration over coordinates here. If it turns out this is also Legendre polynomial, it simplifies our life, because then the integration here over the angles, we can make use of the orthogonality of the Legendre polynomials again. Okay, so this is the formalism. This is how we end up in a multipole expansion. And now, having given you an introduction again to the questions, let me just see how I get them back here. Here we go. So let me share back. Are you seeing the slides?
Yes.
Okay. And here we go. So now, let's look at this. Two charges here. They're off somewhere. I said you can use the origin in principle, if you like. What is the result of the summation in this case? And you see here, it follows indeed correctly the definition. The arrow points from the negative charge towards the positive charge. We have another 10 seconds about. Okay. Plus QD. Well, we went just through it by definition, the way I add them up. Because of the definition, we started out as 1 over the distance to the positive charge minus 1 over the distance to the negative charge. And if I then turn this into an approximation, we saw actually it just ends up being q times the distance. Now, in this case, unlike the way I put it on the whiteboard, the origin is somewhere else. Nevertheless, because we only depend on the distance between these charges, or given by the vector between the charges. We call this a coordinate system independent formulation. We concern ourselves to put a coordinate system there after the facts are and unfold this in a formulation or in a calculation explicitly to a reference point later. So what is the magnitude of the dipole moment of this charge distribution? Oops, sorry. Why is it 2QD? Yeah.
Because the charge is 2Q on each of them, so therefore it would have 2 times the dipole moment.
Yes. Or if you go back, how we got there, we multiply out the charge in front of the bracket before we sum up the distances, 1 over the distance. Yes. And here you see the QI I can take separate. Just as a reminder, so this is the way you wrote in your homework, where you came up with this coordinate independent formulation of the potential for dipole. So in this case, we have to plug in Q 2q and then the vector d times r. And then again, if we have chosen d along z, then it is z unit vector times r unit vector, which is cosine theta, the polar angle. This is finally when we made a choice. So, explicit evaluation. So then in this case, what is the dipole moment of this system? Does it have one? QD again. Why in this case?
Dr. Spanier, I'm actually not sure. Can you explain it? I feel dumb for asking, but I'm kind of confused as
That's
why
good.
it's B. I'm so sorry. I feel bad.
No, that's correct. That's okay. But why does it come out 2QD to begin with?
That's can I try to take a guess real quick before you give the answer?
Yeah.
Because this actually has to do with the question I wanted to ask you when we got to it, but I guess this is it. Is there a dipole moment because two of them or the charges neutralize, however there's one q that's left over,
right?
And because it's separated by a distance, that although it has no other negative charge to have a separate distance off of, is that why there's still a dipole moment? An extra one?
Yes. So you expect, like you said, there's a monopole moment, but it doesn't preclude there is not a dipole moment, or even more, but in this case it's just a simple separation. No? So yeah, we expect some dipole moment, but it is curious, no, that in this case it is 2QD. How do I arrive there? I use the definition we just wrote down there on the previous slide, no? To get the dipole moment, I add up the QI with the RI prime. Let me see if I can flip back. I do not reset the question, but if I go carefully backward, I will not start the question again, so don't worry. But if you look at the definition here, no, it's just QI RI. And so in this case, the RI for the negative charge is what? The RI prime, sorry, is what?
0.
Yes. And so what's the problem? That I put it to 0, you may say. But what's the deeper problem here?
R tilde is actually just the R vector for the positive charge.
That's right. But I'm saying it's even a more systemic problem.
Do we have to make it a neutral charge by like considering a mirror charge?
No.
Okay.
No. The problem comes with what I started out with. You can use to advantage, pull the origin in the middle of the charges. Yeah, so that when you do the integration, you really run first inside the cloud, you add up your charges. Or in this case of the dipole, the best point seems to be exactly between the charges. So you can formulate this really the way we did, or you arrive at the expression we did. But there is actually dependence on where you put the reference point, where you put the origin. No? So you get a different answer here, dependent on where you put the origin. And that's a systemic problem or a systematic problem in doing a multipole expansion. You have to be very careful where to put the origin because your answer depends on it. So the outcome here to be the same as from the previous one was by the choice of this coordinate system, not because of the physics. So that's an important realization. That's why I left this question. So if you were confused, that's good, because that's exactly what you should be or what you should be careful about, let's say. Yeah. And let's go back to this a dipole. You also went through the exercise to get the field. By definition, no, once you have the potential, that was the whole point to start out with potentials, because we can then come to the field by using the definition that the field is minus the gradient of the potential. And we arrived at this expression. There's a theta and there's an r dependence. And so for a dipole at the origin, here it is spelled out, pointing in the z direction, the electric field strength is given as, and theta indeed is now the angle with respect to the z-axis, or our familiar polar angle. So what does the formula actually predict for the direction of the electric field near the origin? Did you answer differently? I hope not, because that's the whole point, no? We want to go far away from the origin.
I didn't catch that little last part right until you said it at the end, that it was actually close to the origin, not far away, because we've been doing so many. If it was far away, it would not have been that answer. It would have been up, right?
It depends where you are, no?
Okay.
I show you the picture one more time on the next slide, but yeah, the very basic is, of course, it doesn't apply in this region. You cannot use it, no? By construction, we said we go far away from it, and then it is a good approximation. Yeah, and even so. I wanted to show it to you now. Here we go. Yeah, so by ideal, I mean the one plotted as the formula describes it. But you see the electric field lines. Oops. Just a second. You see that the electric field lines indeed turn inward, close to the origin, and in a physical dipole on the right side, if you look very close, slightly to the outward, this is still the case. So the formula really only describes the dipole, physical one, if you go out of this region. Yeah. You see the field lines actually turn sharply in here. This is not the case for a physical dipole on the right side. Okay. So then let's just look at which charge distribution below produce a potential which looks like C over R square when you're far away. And then one, no? These. We discussed it. No? Why these? Now this one is straightforward. The B one is straightforward. C, we know it doesn't. The one on A we just discussed also has a monopole, 1 over R, and it will dominate, of course. And then the one on the right, because actually as we zoom out, the 2 minus Q's will come close together, and then again we have the situation S and B. Yeah. Let's just quickly see how we formally deal with distributions like this. So let me see if I can again project. Do you see the whiteboard again?
Yes, we do.
Yes.
Okay, thanks.
Dr. Spanier?
Yeah.
I want to ask, are there 3 types of dipoles from what I'm gathering? We have the pure dipole, we have a physical dipole, and then let's say I personally myself, I'm standing at the origin and I have a charge in my hand and I throw it like a football. 1 charge. Does that create a dipole moment for a certain amount of time?
Okay. Short answer is we are in electrostatics. We don't throw charges around. The long answer is you're right. So if I make the charge move up and down, I get the time-dependent charge position, and then I create a time-dependent dipole moment. But you have to be patient. Along the lecture, we get there.
Gotcha.
Right now, we just fix them. And here's an example. I think I'm losing this one. Here's an example of a placement of charges. And I'm just going to apply the definition. So this is 3Q, this is Q, and then I have minus 2Q and minus 2Q. And they're all a distance A away from the origin, and this is the y plane. So in principle, X is this way, but there is no charge placed along X. So we are talking about a 2-dimensional configuration. So first of all, of course, is there monopole contribution. I made the choice here already where I place the origin. I place it in the center here. Is there monopole?
No.
Because?
All charges are accounted for in terms of neutrality.
The sum of all charges is 0, no? Yeah. So if I step further and further away, they fall together. Virtually, I have 0 charge. And then, what about dipole moment? By definition, just to write it one more time, this is Qi Ri prime vector. Do we expect the dipole moment in this case? How would you argue?
I would say no, that there's no dipole moment term.
Because?
Because, well, okay, I don't know. When I think about it now,
Yeah.
there's gonna be some arrangement of the dipole moment. There's
Right?
I don't know if they would cancel.
If you look at the last question, no, where I put the 2 minus charges a bit separated, but still in a positive charge. If you move out, you see actually there is some imbalance here, no? I put 3 positive charges up here, 2 negative charges here, and only 1 positive charge is here. So you would expect there is an imbalance here in this direction. If we had to guess which way the dipole moment goes, something sticks out this way, Because down here I was putting more emphasis of negative charges. Up here I have more emphasis on positive charges. Or if we become explicit, of course, we can guess all day. We can also just plug it in by definition. It's the sum of the charges. And so it's a vector. Nothing is going on in X. So if I do this in Y here, so I have minus 2Q at plus A, and then minus 2Q minus A. Oh, be careful as a vector. In this case, we're going along Y, but the sign here is in negative direction. And along Z, this is 3QA plus the 1Q down here, and this again with a minus A. So it becomes 0, 0, 2QA. Indeed, what you guessed, the dipole moment indeed points up along Z and has a finite value QQA. What's the potential? If I were now to write the potential for this, in approximation, of course, because it's a dipole moment. By definition, we said Q P R over R square. And so if I plug this in, it becomes K2QA. And then Z unit vector here times, because I could have written this as T QA C. So I'm here ZR. This is cosine theta. But only because of my choice here of the coordinate system, and then divided by R square. There you go. We even got the potential out of it, so it's straightforward now. What about quadrupole moment?
There would be a slight quadrupole moment, but the dipole term would dominate since it exists.
Correct. Yeah, because the next one goes with 1 over. In terms of potential, the next one goes with
1 over r cubed.
Right. And let's see, time. One continuous example we had actually discussed in several ways by now is spraying a certain charge distribution over the surface area of a, let's say, insulating spherical shell, sphere, shell, radius r. This is too close to the top here. And I choose Z through here, so R. And if I misuse this to also indicate the radial direction, then is the polar angle measured with respect to the origin down here. And so I put some area charge density on this shell, which we discussed could look like kappa cosine theta. And we found for the potential outside, using our ansatz, no, because of the boundary conditions, we know it has to this BL contribution in the formula, and we arrived at the potential this way, an exact formulation. And by chance, it gave us a potential which is already 1 over r squared. We didn't identify this explicitly as the potential for a dipole, but it looks like a dipole. No? We put a positive charge on the kappa, which includes charge in the right units, of course. This cosine theta, meaning somewhere up here it is more positive, and somewhere down here it is more negative. So indeed, even just looking at it, it looks like a dipole. So how do we get this? Now we can go back to our original formula. If we were to plug in, just as a reminder, if I were to write this down as a 3-dimensional charge distribution and just plug it in, no, then the rho, in this case, collapses to the theta and phi dependent one, and then I could write it like this, just as a reminder, instead of immediately manipulating the integral and knowing I only integrate over the surface area. If I'm very formal to use the definition, then I can also do this. So the integral, which I have to evaluate for the dipole moment, we wrote this 2 whiteboards ago. In this case, this is z rho d tau. And because I used now this definition here, it becomes C sigma R square. Don't be confused. I really just want to sneak in one more time. We can start really dogmatic from the expression we wrote down once, and then just collapse it this way. And then d cosine theta d phi, of course. And to get this C out of here, we use z over r. This is just cosine theta, and plug this also in. Yeah. So the integration becomes relative straightforward on the phi. It's symmetric around phi, so this gives me just another 2 pi out here. Because I plug in Z over R here. I plug the Z as R cosine. I get an R to the third power out here. And I'm left with cosine square inside from -1 to 1. I'm crowding my right here. So here I plug in R cosine theta practically for Z. So I get this R to the third power, and now I plug in this. The kappa, of course, still goes here. I have a cosine from my sigma up there. And I have the cosine from here. So this gives me a cosine square theta. And then integrated the cosine theta. You have guessed this already. We don't necessarily have to do this because we know this is just, or can be rewritten as Legendre polynomial here, and we knew this is just Legendre polynomial integral here of the first one that survives. And so you can take the factor which we get now from the integration, actually just from the Legendre polynomial formula. No, this was a 2 over 2L plus 1 factor. L is equal 1, so it's a 2 over 3. But I'm just saying that because you can also, of course, easily integrate cosine squared to cosine theta. But this shows the relationship in what we did before, and non-surprising, we get an expression as we got before. Let me just see that without going through the details here on the whiteboard, just copy this correctly, hopefully now, times 2. 4 pi r to the third power over 3. This is actually just the volume of the sphere times kappa. And so if I plug this in my expression for the potential now, indeed, it becomes k 4 over 3 pi r to the third power. I can just hiding the volume here. The kappa cosine theta over r square. So this is the term, the potential we get in the dipole approximation of this distribution. What about the quadrupole term? What do you naively expect about a quadrupole moment for this?
For a charge distribution, I mean, the dipole term is going to dominate, but the rest of the terms would exist. It just depends on how accurate you want your answer to be.
How accurate is this? No, I slipped this in while I was explaining it. You guys, I said this looks exactly like what we derived 2 lectures ago, before the exam. If you go back at the expression where we found the coefficients, we used the answers for the potential outside. No? In this case, the BL survived, and we found from the boundary conditions the factors here. But if you go back, it looks exactly like this. Constant, say, times cosine theta over r square. Now in this case, we went through the exact exercise. No? We would have continued adding terms last time because we used Legendre polynomial orthogonality. We get the precise answer because we allow the sum in principle to go to infinity, but because of the configuration, because of this particular choice, I just mentioned it now, this is P1, we were left with only one term, which looks exactly like this. which means the exact answer is that. What does it tell us about higher multipole moments?
Their contribution is insignificant.
No, it's zero. It's exactly zero. If I'm telling you that the precise evaluation of the potential gave us this term, and the approximation outside gave us the same term, that means we don't have to continue searching for higher order terms. Does it make sense?
Yes.
Yeah. Last time we didn't make this approximation. We used what we found is the exact answers. We used uniformity. We used the uniqueness theorem to convince ourselves that's the solution last time. And now, by using this approximate method, we find it looks exactly like this. So it means we have the unique answer here, and there is no more.
Dr. Spanier, real quick.
Yeah.
That last line on the bottom there, I just want to confirm, and I'm pretty sure this is very elementary, but you have the integral of cosine squared to d cosine theta. Because it's d cosine theta, we can just say, cosine cubed over 3.
Correct.
Okay.
Yeah. Or you can call it substitution. I substitute cosine with u, so it's du, u squared du, which is u to the third power over 3.
Conservation of variables. You can use that u for something else.
Sorry?
I was saying conservation of variables. There's not many to be had, so you want to save them.
Yeah, fine. But that's just our math tool. You could have guessed it, huh? By using orthogonality here. All right, that's what I meant. You don't even have to necessarily do this particular integral. But that's up to you. That's how, so to say, fluent you become in this, doing these kind of things. One of the objectives here. So let me go back and share the slides. I see we run actually a bit out of time. I wanted to open the magnetostatics. Let's see. Okay. So why not C is obvious? We discussed this in the very beginning. No, the dipole moments obviously are vectors, and we just went through the exercise. Now you can do it by yourself, and they add up to 0 in this case. And I did that. So very last, let's just do it. So there's a configuration here of charges, plus and minus. And the question is, in terms of a multiple expansion, the following charge is, and then mono plus dip plus higher, dip plus higher, just dip, or a dipole, and then only terms higher than dipole, or no higher terms. VR is 0 for this one. Maybe this was a bit too fast now. I hit the timer. One thinker. Let me recast this question. Oh no, you got the answer. Okay. The answer is only higher terms, no? We can add up the dipoles here, as I just said. The total charge is 0, no monopole. The dipoles add up to 0, and that means we get higher order. This is a view into the Large Hadron Collider ring in Geneva, or near Geneva, outside of Geneva, 150 meters below surface. You may have heard about this. The important thing is why I show you this is what you're looking at are actually very strong magnets. Strongest magnets at this size built in a laboratory. It's superconducting. And we will address what superconducting.
My dog Callie.
I assume you have heard about
She died when I was 8.
superconductivity, huh?
And
But we will address
crawled
it
on
again when we talk about resistance in
the porch.
conducting, say, wires.
To me alone.
This is one example where you use magnets. And in this case, you direct free proton beams or current of protons around the circle. You see the thing is bent around the corner in the far. So in this case, to really show you, there are a lot of magnets around. There are 1,232 dipole magnets, which gives you an idea why I insisted we finish out chapter 3.4, the multipole expansion, because we, of course, will be faced again with it when it comes to magnets. And indeed, you classify their field in terms of multipoles. So, simple one is a dipole,
To be alone.
a higher order one is a quadrupole, and they have different functions to deal with this charge current. And we will all discuss this. But magnetic fields are created by what? Just one fundamental statement. What are magnetic fields created by? Are you busy or are you trying to answer this question? Let me pause this. Let me see if I can pause this before we continue on this question. You can try to answer it, but I want to quickly give you the fundamental introduction in the last 7 minutes. Let me stop sharing. Let's quickly jump back to the whiteboard. The basic answer would have been by moving charges. Now I just stopped. I don't know who it was, but I just stopped somebody asking on the time-dependent dipole. And I said we are discussing only static charges. Now to a point. To understand magnetic fields, we actually have to talk about steady flow of charges. For example, through a wire, conducting wire. And they're not exactly straight, but let's say I flow charges this way. I have some velocity here, and it goes up. And on the right side, I actually connect these wires. I let this current continue, but then it flows down here. Instead of talking about charges that move with a velocity, if we have a bunch, we don't care about individual ones. We call this rather current or I current. And so I could have also written down here, this is I. Now, if I wanted to still keep track of the direction, I would have to put an arrow on top of the I. We have one simplification here because the I can only go where the wire goes. We keep track of the direction rather which way the wire goes. So later we will just follow the wire with little elements dl. If it's straight, then of course it becomes just dl over the length here. And so for now, I just keep it as magnitude here, I. You have seen this experiment. What's going to happen with these two wires? Have you? What happens if they're close enough? I run this current up and down.
They should repel each other.
Why repel? This one goes here, you say, this one goes this way. Which means there's a force at play. Why? Repel? How would you argue?
The magnetic fields are opposite with both wires. Or the magnetic force. I'm sorry, magnetic force.
The magnetic force is opposite, yeah. But next question is, where does the force come from? What creates this force?
The movement of charges creates a magnetic field, and the magnetic field creates the force.
Okay. So
Magnetic field doesn't.
Yeah.
I thought the magnetic field didn't create a force because it doesn't speed up the charges and stuff. Like.
So let's start step by step. So the moving charge creates a magnetic field. Okay. Right. So up to this point, I think we can agree.
Yeah.
Which way does it create the magnetic field?
Perpendicular to the velocity.
Okay. And so if I were to indicate the field here, which would mean I need to now use the same concept I used in the electric field case. I would go with an elementary charge, move around here, everywhere, check which way it is pulled, and indicate this, and arrive at a field map, a mapping of where the force goes everywhere. In this case, I would use a compass or a little compass, It has a south pole and a north pole. And it will react to the magnetic field. So I can go here and move it through my configuration. What will I find? The magnetic field goes. Let's use the spot to indicate it. On this one wire, it will be. If I start drawing the field now here, I call it the magnetic field strength. The same as E for the electric field. No, it will be circular. Wherever I go around here, the compass will always show tangential here. The compass everywhere where I go will actually point like this. So I can go around in a circle and it gets pulled with the same strength, let's say, in each of these points. So the next would be like this. In the plane perpendicular to the velocity, correctly said. So, in fact, they have an orientation. By definition, I define the directionality here. You have seen the magnetic field. If I were to probe a permanent magnet and I go around, the field goes from where to where? In case of a permanent magnet, if I run with the from north to south, so the same way. And actually, what you see here looks awfully like the dipole field we just discussed. No? In fact, we call this a dipole, a magnetic dipole. We will discuss that the field lines do not terminate. We are stopped here now. They will continue throughout this magnet. So inside they will connect south to north. So the field lines in this case, circular, and we don't have to remember the details. We can call this out with the right-hand rule. Or we can find this with the right-hand rule. If I point my thumb in the direction of this current up here, your fingers curl in the direction of the field lines. In fact, B is proportional V cross, in this case, I said sorry, the force. V cross B. So force, the velocity, and the magnetic field here are connected via a cross product, as is the magnetic field itself. But we come to this. And because I can write this also as an I cross, I can apply the right-hand rule. Like I said, I come to the explicit dependence here. Simple relationship you can already infer is the higher the current, the higher the magnetic field. We definitely have this current dependence. So the right-hand rule gives us the direction of the magnetic field. So it curls around the wire here, and accordingly, somebody said this already, it would curl the other way around. You realize this is a mutual force. So we want to rather formulate this as a moving charge on this side in the magnetic field of this side. The force is the same, no? It's mutual. If you set it up like this, which by chance is set up to actually measure a current strength. To define an ampere, we could actually just measure the force between these wires and how strongly they repel, like I just said, it is proportional to this current. Okay, so we measure indeed the effect of a charge moving this velocity v in the magnetic field of the other wire. Complete this here. The full expression for the force is Q times V cross B, which is also called the Lorentz force. So again, I apply the right-hand rule here. So V goes down, and the magnetic field now I would have to draw this circle further out. No, it's tangential. In this case, it goes this way. V goes this way, and now we have to use the right-hand rule, which tells us what happens if I rotate V on B. You can try it with 3 fingers. I prefer the slightly simpler version, which I already just used to find the direction of the magnetic field. You just follow how you curl V, how you move V, not curl, how you move V on B here. So in this case, I would have to push it back, and my thumb points to the right. And indeed, we were right. So at this point, we did not derive it. In this case, the force would go this way. And if I flip the situation around, accordingly, you find the force on this side goes the other way. So this is a couple of basics. And I want you to read up on the magnetostatics. So next time I can speed up, but after we discuss it now, let's just finish that question I opened for you. So in this case, a proton is released from rest in a uniform electric and magnetic field. We of course know the electric force is just Q times E, F equal Q times E. If E points up and B points into the page, which of the paths will the proton initially follow? Let's say you put it somewhere in the middle of the setup on the left side and let go. The magnetic field indicated here goes into the page, and the electric field points up. Now you have to remember what the electric field direction means. If I put a positive charge in this, which way does it get pulled? At that point it moves, and the moment it moves, the velocity in a given magnetic field, if it is perpendicular to the direction, it will be bent, it will be pulled one way or the other. Okay, so having said all this, Did you find this? Yeah. By definition, the proton will be pulled up, first of all. And now we have to do the right-hand rule, what I just did. Curl the V into the B. And in this case, you find it goes to the right. No? Okay. Thank you very much. And I see you on Thursday. If there are no... Actually, are there any questions? No questions. Then I see you on Thursday.
Thank you. Bye.
Bye.
Have a good day.